Good afternoon, everyone, and it is a real honour and a pleasure to be here. Certainly, I remember visiting DLR many years ago, but to come back here and to see how it's been transformed in recent years, and with all the new facilities and the demonstrations yesterday were fantastic, and congratulations. Good. I've got to say that I bring you good tidings from everyone in Australia. I know you've got a lot of good friends there, like people like Ray Jarvis, Peter Cork. They all send their best to you. And I guess that for me, I've got to say that you've always been one of, I'll be honest, in sort of like melodramatic terms, one of the heroes, and a real inspiration for all of us, and certainly for our field. So, and I must say, I've always watched your work to be inspired, but also to be careful not to do the same things, because I know if I did it, you would undoubtedly do it better. So, so making sure that I was in a non-competitive area. So, I guess that I've been sitting here for a day and a half listening to these great talks and thinking, my goodness me, the bar is so high, so many fantastic talks. And then I had to sit with Greg Hager in the bus last night going to the dinner, and he's telling me how much time he'd spent on his presentation and what he was going to do, and he'd really thought it through very carefully, and I'm thinking, oh my goodness. So anyway, I had some jet lag last night, so I worked for the presentation. But anyway, if I think about the grand vision of robotics, if you ask anyone, it's about, if you ask when we all started in that field, 50 years ago, it's robots everywhere doing work for people. That's where we always thought it would be. However, I think that the vision is changing in a somewhat, but to me it's actually robotics everywhere. And instead of robots populating the environment, I mean, we saw some fantastic talks before lunch from Professor Inouye and Professor Inabar talking about the robot, but actually I think there's something more there. Our technology can go everywhere in the environment. In other words, robotics is, like as Michael Brady says, intelligent connection of perception to action. So that actually opens up a whole vista of opportunities where we can have robotics. So you imagine, instead of a humanoid robot maybe driving an ordinary car, you could have the car being a robot of sorts. And going further, I think there's interesting ideas of these sensor networks, which are small devices, which are got microcontrollers, radios, and sensors, populating the environment and working together, gathering information. And that actually creates a very interesting new paradigm. So you can sense and they communicate to each other. Then there's, from some gateway go to and maybe control soil moisture. And you can precisely water on a farm exactly where it's dry. So that's a kind of classical model, but actually with robotics everywhere, I believe that we can change this paradigm where we actually compute inside the network and actually act and do the actuation, rather than pulling information off, sending it centrally, etc. So these are the sort of things which are now possible with the robotics technologies that we have today. So it's in-work decision-making and actuation. I actually put this slide in a video. I know that when most people know me, know that I've never done much work in humanoids. And I always said, I can't find an application. I have an application, finally. And this is actually what we're doing with the Australian Institute of Sport. We're helping train athletes for the next Olympics. And what it is, we've captured all the motion of the swimmers, and we have a full computational fluid dynamics environment of the water. And actually, you can actually analyze how the swimmers swim. And using the work of my colleagues in the humanoid area, we've been able to actually control the swimmer to see if they change the stroke, can they actually go faster, so the coach can actually coach. So I think now this is another form of robotics everywhere. Actually, robotics in simulation for human performance and judging machines. So this is, I've been very excited about this. Normally I couldn't find an application in Australia. We're very practically minded people. So someone has to pay for the research. So we've actually been able to get this. So when you look at the Australian swimmers in London next year, look for the gold medals from us. So anyway, and hopefully this technology contributed. So, but really, what are we trying to do with robotics? It's robots for service. And I think we have to remind ourselves why we actually want to have robots. I think a lot of times when I started, and many of my colleagues and my students started, it was just to build something cool and be just doing very nice things with technology. But at the end of the day, if you really want to actually create technology for society or for the markets, you've got to do something more effectively, efficiently, reliably, and safely, and deliver a service of value to customers. Someone will actually pay you for it, or a company, or somehow you do this. And I think those things, we sometimes throw away those 4 things at the beginning. Don't want to do it reliably. Well, if you can't do it reliably, it's probably not going to be of much use. And safely is the other very big point. And I heard that in some of the talks this morning. So, and I think that, we look at there's a couple of examples there, of course, the iRobot, and then, of course, I think one of the great examples of a robot is really the elevator. Many years ago, people had to have an operator to take you up and down. Now these things are quite intelligent, and they can communicate to each other. They can determine if it's too heavy, when it needs to be going to maintenance. They can optimize their schedules and control each other. Quite an amazing system. Very reliable, efficient, and safe, and creates value for customers. So that's the kind of thing we should be aspiring ourselves to. We might not think of an elevator as an intelligent robot, but actually in my bones, it's robotics in the environment. It's actually got all the characteristics of what we look for. So these are the sort of examples that we should be seeking to match. The other one I think that people always look at is the safety and liability issues. I know that Sebastian's doing fantastic work now for Google with the Google car and after the Grand Challenge, etc. But there is a real fundamental problem here. Who bears the risks, liability risks? And this is something that you really want to understand if you want to bring a product to market. Is it the public? Is it the manufacturer? Is it the owner? Or the person who operates? Generally what's happened in all sort of automation and technologies, the manufacturers have been able to shift the liability onto the owner or onto the public. And so if you actually create this technology, you must actually be very, very sure that who takes the liability. And currently I think that Google has to take the liability. It won't be the car company, it won't be the driver, because you're not driving the car, something else. And this may actually limit fantastic technology going forward. And I think one example that we can think of is like pilots. We have autopilots. You can actually go in a plane and the plane would fly without a pilot. But do you think anyone would get on a plane without a co-pilot or pilot? And the answer is no. And it was a great example with the Qantas A380 over Singapore. Its engine blew up, and it actually caused a lot of mechanical damage, and it was only the pilot's skill that landed the plane back. And I think we have to understand, so if there's humans at risk, can we have an autonomous system? In fact, this system's here, we're talking about airplanes. We've got an autopilot, a pilot, and a co-pilot who actually assist the pilot and can take over in dangerous situations and relieve the load. So we have to think about systems that are already in place and think, can we truly make them or replace them? And I think we have to think about it from a liabilities point of view. Okay, but the real thing is, why we want to do things is to solve real problems. And for me, it's about what we're going to do for robotics is yes, it's lovely to build cool technology, but it's got to be something for make the industry more efficient, society fairer, or looking after aged people. It was very interesting. Last night at the Deutsches Museum, I went upstairs with John Hollerbach and who else was there? And we went up there, and there was wheelchairs up there, and you could ride the wheelchairs through the gravel and through the slope, and it was only 6 degrees. I didn't realize how hard it was to operate a wheelchair. And I think there's lots we can do, and the same goes for elderly people. There's a lot we could do with our technologies to help people. And lastly, the environment. We are actually at risk of overconsumption, and I think robotics could actually play a big role in this place. So, field robotics. That's one of the things for us in Australia is we're a small, relatively small country. Large landmass, only 22 million people. So we have to find a competitive edge where we can apply our robotics. And we've actually settled on field robots for service. In other words, big applications. And my colleague, Hugh Darrant-White, was quite well known for all the work he did with the automation of the cargo handling and unhandling. So, and what are we talking about here is really developing technologies which allow people to replace people doing difficult, repetitive, or unpleasant tasks, very much usually in dangerous environments. This has really become a field on its own. It's now even got its own journal. Last 4 or 5 years, it's come up and quite strong on the impacts, and I think it's really pleasing to see the technology move into these applications in tough environments. And usually we're talking about operating in complex, dynamic, unforgiving environments. And this is an example of one of the systems we built, which was quite a small robot. It's not much bigger than this table, that you could actually use for subsea mapping, or actually in shallow environments, but it's a totally vision guided system, and was recording data and then coming back. So, but where we've really had our roots is in, and a lot of this work was done by Peter Cork, my colleague and friend. And Peter and some of his workers, they worked on this dragline automation. This crane here, it's not a crane, it's actually a machine here, a dragline. This is actually a 3,000-ton vehicle. That boom is 100 meters long. They automated that machine and were able to dig. And we had to do 3D mapping of the environment and digging and control. And I'll show some other videos of these things. And basically, we've been looking at these systems. They don't operate on their own. There's a driver in there, but some of the functions are automated. So it's people and machines working together. It's not an autonomous dream. Although there is the idea that one day the mine will be totally autonomous as each function is automated. But that is a long way to go. But we're moving that way. And we've done quite a number of different experiments in this area. And some of these systems are now gone commercial. This is one that we did. It took 10 years. 10 years ago. It was and this was basically one of these load haul dump vehicles, LHD. And basically you could drive through a mine, delivering material that it picked up and dumped. And so this is really just basically corridor following, nothing more than that. And we were using 2D lasers at that time, but it had to take branches and navigate through the area. But this was back then. We didn't have the mapping technologies that we have today, but nevertheless it could actually navigate quite robustly and became a commercial reality. And now it's being sold by Caterpillar to mining companies around the world. But this is a basic sort of task. So what we've become more interested in is more in the operating in 3D environments where there is no corridor to run through. So you need to have a variety of sensors. And we're looking at redundancy of sensors. And we've used vision and lasers and GPS and tried to fuse many of these informations together. But interestingly, of late, the laser sensors that have, and I noticed that Professor Inoue was talking about using the laser sensor to scan the environment for the robots to walk. And I think the lasers are now starting to almost beat out the computer vision in terms of sometimes, in terms of performance that we're seeing. And also with the RGBD systems like we see with the Kinetic from Microsoft. So fantastic technologies emerging there. One of the things that we've been really interested in is systems that can operate in the long term. Can a robot operate continuously 24 hours, 7 days a week, and without people around or with limited interaction with humans? So we've actually tried to run our machines for long times, trying to actually understand what will break in them. And quite often it's software. Software is the thing that breaks first. Many bugs that we find or design faults in our systems. And so basically looking for ways to degrade, or when a sensor fails, what do you do and not to have accidents? Because these sort of machines, if there is an accident, they're quite big, it can actually cause a severe aspect. And it's a great way to test things. So this is an example that just ran for a day. This thing is moving around in a compound, picking up and delivering a bucket using computer vision and lasers and things like that. So it ran all day, different lighting conditions and things like this, and people wandering in and out, and it had to stop and things like that. And these sort of experiments, they're not that exciting to conduct in terms of the students, but they're very important to do, because if you want to have dependable systems, they must actually operate for the long term. And we've had to actually undertake a lot of understanding of, it's an engineering task, but it's also actually tests the operating bounds of an algorithm. Quite often we actually make an experiment in a laboratory over very controlled conditions, but when you put it out into the real world, the conditions change. So this is so it's testing, but actually, and then we can refine. So this is actually an example. So we'd make a map, and you can see this is in real time. Actually, was using the lasers here to construct. And there's a little line running along the dark line. It's actually a person walking beside the machine, but you can see that it's actually moving along, and the person appears in front, and it'll actually stop, and then the other person walks around to see what's going on, and etc. And they walk around, and it's still the machine actually detects all this, and it actually senses around the machine continually. So this is a very large machine for it's basically a forklift, but a very big one, about 16 ton. Okay, one of the things that this got us interested in was these lasers, and obviously the great work that's been going on in SLAM. And fortunately, we've got two great guys that work at CSIRO, Mike Bossy and Rob Zlot, who work for me, and they became very interested in this this method. And really, it's the scan matching of trying to take data and trying to solve simultaneously the localization mapping problem. It's all been done before, but I think what our guys have done now is be able to build these maps on a large scale and very accurately, and not require any other sensors. So in this particular example is a vehicle with a laser pointing front and back, scanning and driving around a Brisbane suburb. So and this is just a continuation. That first grid I showed you was 1 square kilometre. And now it's actually driving out. It's a bit hard, the video jumps around a bit because of the scaling changes here, but it's essentially the map grows. So the guys drove around in the suburbs around the city, 165 kilometres, and the map was built and designed. So it goes, and as it moves through, it actually closes off the loops and the inconsistencies. The other important point here is no GPS, no inertial navigation unit, no odometry, straight matching of scans of lasers. So what you can do is do quite amazing maps. I couldn't believe this when they first showed it to me. So this just shows how this technique has developed, and it'll play on. The really impressive thing is, if I show you the next one, this is the map we took out from from what you can buy, or from a proper map, and then overlaid the map that we made with the SLAM, and it sits right over the top. So quite good. So we've now taken this further, and then took that laser, which is a 2D scanner, and just put it on a motor and created a spinning laser. So it became like a 3D spinning through, and you could actually get a hemisphere constructed from this. And here's some examples of this at work. So this is that same environment where that machine was operating in before. So straight away we're actually able to move and construct, and you can see how well this scan matching is moving. It's actually matching up the point clouds quite well and constructing this environment. And this is actually now in an off-road environment. This is trees. So with this laser being pointed at trees and spinning around, it's actually reconstructing down to almost the leaf size of the leaves. So you can really construct amazing point clouds and data. So once you have these can create this set of point clouds, you can then create systems that can actually use these and be driven by them. So I think this has been one of the big problems in robotics, for field robotics, has been the perception problem. But I think we are very close to actually solving the perception problem. There's another problem, how to reason with all this and how to actually optimize this information. But I think that's going to be another challenge, but nevertheless, the perception problem in this case is being done. What's interesting here is with, again, just a spinning laser, starting off, it was basically at a mountain, well, no, a small mole of a hill behind our facility. They drove around and down the hill and through the car park, etc. And you can see the elevation map actually being generated. So it's not just generating a 3D point cloud, it's actually generating simultaneously 6 degree of freedom positioning, as well as 3D location and mapping. And this is another one example where we mapped an underground mine, 17 kilometres in 2 hours, and you can see it's a full 3D reconstruction of the map. We've now actually, wrong way. We've now actually done it for 3D street mapping, so mapping of streets, and also indoor buildings. And in fact, we've got a small version now, so you can literally hold it in your hand. It's a bit hard to see, and just wave it around on a spring, and actually reconstructs. So here's it's now been we've actually commercialized it with Trimble, and this company is now using it to map infrastructure, like prisons, military facilities, for security. So you might map the building one day, come back another day, do the map again, then subtract the two maps, and then you can see if someone's added or changed something to the environment. But also it creates the maps now that you can drive robots along with. And this is the things we've been doing with. So I guess that one thing I've been quite interested in personally has been in this driving of cars. And I believe in the co-pilot model. I don't believe in this autonomous vehicle because of the liability issues, quite frankly. That's the issue. But the thing is that the car can do more and more for you. So what you really need is the person has to be put into the loop. In other words, you've got the vehicle, and the vehicle is interacting with the environment. There's sensors measuring the environment. There's some fantastic work that's been done here in Germany over the last 20 years. Started with Professor Dickmans, and has been continued by people like Uwe Franke, who's here from Daimler, and wonderful type of work. But I think what we need is not only just sensing the environment, also need to sense the driver and understand their interaction. Hopefully I'll just show you some examples of why you want to do that. So there's many systems that have been done, things keeping the lanes, lane tracking, detecting pedestrian, detecting objects, reading road signs, reading traffic lights. This is all kind of done. Google's doing those type of systems. And what we want to do is actually see what the driver's doing at the same time. Did the driver notice the red light? Are they going faster than what the speed limit is indicating? If the person is looking at a pedestrian, maybe you don't need to tell them there's a pedestrian ahead. This idea of putting them in, or if there's an emergency, it looks like there's going to be a collision, you can probably take effective action. And so the commercial realities of this, if we wanted to monitor the driver, when we looked at these systems, I should say, when I started this research, we were doing all the vision tracking of the environment, but there were many people trying to do that. But there weren't many people doing drivers and doing that well. So we decided if we wanted to do that well, we should focus on what we could be better at than the others, and we focused on the driver. Interestingly, when we came down to it, I did a lot of, everyone's done sort of experiments, you track some people in a laboratory, face tracking, but here you have to have, if you want to monitor a driver, you need to monitor a driver irrespective of age, sex, race, facial hair, glasses, under all lighting conditions at all times. That's what the business requirements are. That's what you ask the car industry. If I gave you what do you need, this is what they tell you. And which makes it very, very challenging to design algorithms or like to work with that. We still haven't got there, but we're in the high 90%, 95, 98%. So how do you do this? And this was actually sent off a whole bunch of research. So we actually started with the idea that maybe everyone seems to be able to write an algorithm that works most of the time, but not all the time. But what if you could actually have a framework for combining algorithms that work most of the time and maybe create a system that works nearly all the time? So that was basically the design or the insight to our solution. And we have actually built that and realized such a system. But it's been around using a lot of statistical frameworks, writing many indicators. So I'll give a bit of a sense of what the system does here. So basically, in the end, we actually had to make the basic product, the basic minimum product that the industry wanted. It was eyes on road. Is a driver falling asleep or they're not looking at the road? That was literally what it had to be. Had to be one camera and an infrared sensor to light up at night. And basically, we found out that we couldn't sell it into the automotive consumer market, like directly integrated into cars. It had to be less than $250. But as an aftermarket, it could actually be up to $10,000. And we've actually installed it now into the mining industry, into the big trucks. We have now over 3,000 units installed, so it's actually, if you do the sums, 3,000 times 10,000, it's actually starting to become a $30 million market now for that product, and it's actually going onto transportation. So, but what was the basic idea? And actually, I've got to thank, there's people here in the audience that actually inspired me. So we had a lot of feature detectors that we wanted to write to specifically detect eyes, detect noses, detect mouths, detect very specialized features, and also use the idea that a face is actually very structured. We all have got 2 eyes, a nose, a mouth, and there's some average ways that they're actually laid out. So we basically exploit, there is a model. So we actually try to fit a generalized model to the face with these detectors. But the other important point, I've got to start looking at Professor Inouye here, 3D template tracking. You guys pioneered that work, and that inspired me. It was initially 2D, but in 3D, we scale and rotate, and the hardware has now become sufficiently faster. You can rotate and test many matches very quickly and scale them as well and have a pyramid. And this is how the system was built, using these type of methods. And the other important thing what we do is with these products, we continually log data. Look at all the times the system fails, and then try to understand why didn't it fail. And generally it's meant that the model, the face model that we used, gets tweaked or gets averaged out a bit more. We have more history. And we've been able to get it to work better and better. So these are the sort of things that you have to do. The guy in the middle there, I keep, that was the toughest example of initialization of a driver, you know, and very hard. But there's other ones, these are just feature detection, so just for detecting a face and finding those sample features. This is just one part of it, and and just detects, and these are some of the aspects. But the other guy was special. Anyway, but we can see that all the different people we've had to handle over the years. So let me move on. I'm conscious of the time. So with these 3D templates I talked about in this model, it allows you to do rotation, you can do translation along the z-axis, because you have a model, you can cover parts of the model and still match. And also, if you have a model and can predict, you can detect how the model is built progressively. So this is what we've been able to do. And here's some examples. So here you can see this is with the 3D templates. It's actually, the full head has been rotated. There's shadowing going on there. And also, one of the other important things that any system has to do is detect eyeglasses. And they come in various shapes. It's a very different little problem that people wear eyeglasses. If you're wearing eyeglasses, it determines whether you should be, where you look for the eyes and where you determine whether they're leaden fatigued or not. So this is, again, examples. The other important point that we had to do for this system was to solve the gaze tracking problem. And you can see the guys there holding a cup, and the person's looking at it, and the circle that's being drawn is where the gaze is being estimated. And we had to, you have to track the eyelids, the pupils, etc. So we basically were able to show that we knew where you were looking. So when we know you're looking, then you can put that into a car situation, and you can see here is a driving scene, and you can see where the person's looking when they're driving. Of course, then you can start to overlay it with intelligent systems that could detect an obstacle, and then you see, well, was the driver looking at that obstacle? And then you understand how to give an appropriate warning. And here you can see at the pedestrian crossing, the person looks at the pedestrians. Quite interesting. This is all involuntary. The person is driving, and the system is just looking back at you. So this is what we've been doing, and of course there's a calibration stage, but the insight actually was that we did the eyeball was a model there. Basically all humans have an eyeball with basically a radius of 12 millimeters with a very small variance on that. And actually using projections and asking people to look at a known target at the beginning helped us calibrate the whole system. All right. So since then, we've now actually made the system even more robust. So this now is actually, you can get this system, people buy it as an API. This is, I think, now a product which can now allow people for general human-robot interaction. You can just use this system and it'll just lock onto any face. And this is monocular, web-based camera, not 2D stereo, and at actually very high speed, real time, and also feature tracking mouths, etc. So this is what can be done now and used to develop applications. And one of the applications we've been building is 3D displays. And this is where I have to thank Gerd again. I remember we talked about this, and one of your companies here was actually interested in partnering with us, and thank you very much for that. There was a nice business relationship started, and also we've developed the technology further. And you can see there the 3D display has actually been working. So we've now ported this to GPUs and ARM processors, and you can actually do these sort of 3D displays. In fact, we've now actually got it working to glasses 3D, and this is the first product. It was released by Toshiba. It's been licensed into every Toshiba laptop and is now out. And basically what it does is it is a shuttering on the screen, so it projects the image to your left, right, and eye. Because we know your 3D position of your eyes, it can appear to be a 3D object. Just like you used to wear those stereo glasses with the images behind that. So this is what's possible now. And where we're moving forward is also all full-day feature tracking. So we're using one image, that's Barack Obama there, and the other one is, I should finish up, all right. So, and I haven't watched the time, so thank you. And you can do animations. Okay, I want to show one of the last couple of videos here. We have been very interested in agriculture and robotics. So here we are, we're installing these sensor networks. These are live sensor networks. They're on farms, tracking animals, moisture in soils. These have been running now for several years. And they're installed in various places. This is our facility, research facility. That's where we test these things. They're also on dams and also in rainforests, etc., to measure the revegetation of the environment. So it's based on these small processes. But what's interesting is we've built this, but we've also created a whole bunch of sensors, even vision sensors, audio sensors, motion sensors, moisture sensors, and you can basically stack them up and create a system. The system can then be just deployed. You literally drop them anywhere you like, and they discover each other and form their own networks. What's the interesting thing about these sensors is that you don't need to know their position, and that they can be mobile, they can handle failure and rerouting. And this, I think, is a very interesting paradigm. So what we've been interested in is actually putting these on cows and in the soil. And interestingly, like for instance, because in Australia we have farms which can be 100 kilometres by maybe 200 kilometres in size. And the radio can't transmit that far, but you can literally the cattle can go wander around the farm and literally go back and do data muling. When they turn up at where they have to drink the water, there's a data transmitter, they deposit the data and pick up new instructions, etc. What we've also done with these cattle is it's a bit like an electric fence. A cow comes up to a fence, it can be buzzed. We now provide them with a sound that they're approaching a boundary. And the boundary is a GPS boundary. So here we go, this is what we've created, is a virtual fence. So by programming this fence in, the cattle don't go over the line. And this is like robotics, because what happens, I can move the GPS locations, move the fence somewhere else, and we can then move the cattle. Or we can actually separate cattle which is sick and bring them to the vet. One of the things people say, what about bulls? Bulls fight. Well, in fact, we've actually put the sensors on. The bulls actually avoid each other. If they try to come together, they get zapped, just like they do at the fence. I've been thinking about giving this some of my students, I think. Yeah. But you can see that up the top there's the 4 boxes that are getting zapped, the triangles, that's the bulls there. But there's one bull down the bottom hanging around with the cows. He's smart. And the other 4 are away doing their business, following each other around. But all of a sudden, you can actually start to control this environment. And this is one of the things that we're trying to do here. Oops, sorry. I've missed one slide, but anyway, it doesn't matter. It's great work in our team. I've got to acknowledge the people that have worked on this project with me all these years. We've got some great people in Australia, and I really want to thank you for giving me the opportunity to be here. So I'll just quickly wrap up here. I think it's about robotics everywhere, working safely with people. I think rule problems is a good motivation. I think it's more about not just robotics, it's autonomous systems and smart environments, but also thinking of commercial realities. And as we think about commercial realities, this is why we don't have robotics out there in the marketplace, and they have to be designed for human factors. And the other important point is high performance. You cannot walk away from that. and software engineering, frameworks and exhaustive testing and validation. So now I've given you some case studies today, so thank you very much.